In statistics, a receiver operating characteristic, or Roc curve, is a graphical plot that illustrates the performance of a binary classifier system as its discrimination threshold is varied. The curve is created by plotting the true positive rate against the false positive rate at various threshold settings. The true positive rate is also known as sensitivity. Recall a probability of detection in machine learning. The false positive rate is also known as the fallout probability of false alarm and can be calculated as the Roc curve is thus the sensitivity as a function of fallout. In general, if the probability distributions for both detection and false alarm are known, the Roc curve can be generated by plotting the cumulative distribution function of the detection probability in the y-axis versus the cumulative distribution function of the false alarm probability in x-axis. Roc analysis provides tools to select possibly optimal models and to discard suboptimal ones independently from the cost context of the class distribution. Roc analysis is related in a direct and natural way to cost-benefit analysis of diagnostic decision-making. The Roc curve was first developed by electrical engineers and radar engineers during World War II for detecting enemy objects in battlefields and was soon introduced to psychology to account for perceptual detection of stimuli. Roc analysis since then has been used in medicine, radiology, biometrics, and other areas for many decades and is increasingly used in machine learning and data mining research. The Roc is also known as a relative operating characteristic curve, because it is a comparison of two operating characteristics as the criterion changes. Basic concept. A classification model is a mapping of instances between certain classes, groups. The classifier diagnosis result can be a real value, in which case the classifier boundary between classes must be determined by a threshold value, or it can be a discrete class label, indicating one of the classes. Let us consider a two-class prediction problem, in which the outcomes are labeled either as positive or negative. There are four possible outcomes from a binary classifier. If the outcome from a prediction is P and the actual value is also P, then it is called the true positive. However, if the actual value is N, then it is said to be a false positive. Conversely, a true negative has occurred when both the prediction outcome and the actual value are N, and false negative is when the prediction outcome is N while the actual value is P. To get an appropriate example in a real-world problem, consider a diagnostic test that seeks to determine whether a person has a certain disease. A false positive in this case occurs when the person tests positive but actually does not have the disease. A false negative, on the other hand, occurs when the person tests negative, suggesting they are healthy, when they actually do have the disease. Let us define an experiment from P positive instances and N negative instances for some condition. The four outcomes can be formulated in a 2x2 contingency table, a confusion matrix, as follows: Roc space. The contingency table can derive several evaluation metrics. To draw a Roc curve, only the true positive rate and false positive rate are needed. The TPR defines how many correct positive results occur among all positive samples available during the test. FPR, on the other hand, defines how many incorrect positive results occur among all negative samples available during the test. A Roc space is defined by FPR and TPR as x and y-axes respectively, which depicts relative trade-offs between true positive and false positive. Since TPR is equivalent to sensitivity and FPR is equal to 1 minus specificity, the Roc graph is sometimes called the sensitivity versus plot. Each prediction result or instance of a confusion matrix represents one point in the Roc space. The best possible prediction method would yield a point in the upper left corner, a coordinate of the Roc space, representing 100% sensitivity and 100% specificity. The point is also called the perfect classification. A completely random guess would give a point along a diagonal line from the left bottom to the top right corners. An intuitive example of random guessing is a decision by flipping coins. As the size of the sample increases, a random classifier's Roc point migrates towards the diagonal divides the Roc space. Points above the diagonal represent good classification results. Points below the line represent poor results. Note that the output of a consistently poor predictor could simply be inverted to obtain a good predictor. Let us look into 4 prediction results from 100 positive and 100 negative instances. Plots of the 4 results above in the Roc space are given in the figure. The result of method A clearly shows the best predictive power among A, B, and C. The result of B lies on the random guess line, and it can be seen in the table that the accuracy of B is 50%. However, when C is mirrored across the center point, the resulting method C is even better than A. This mirrored method simply reverses the predictions of whatever method a test produced the C contingency table. Although the original C method has negative predictive power, simply reversing its decisions leads to a new predictive method C, which has positive predictive power. When the C method predicts P or N, the C method would predict N or P, respectively. In this manner, the C test would perform the best. The closer a result from a contingency table is to the upper left corner, the better it predicts. But the distance from the random guess line in either direction is the best indicator of how much predictive power a method has. If the result is below the line, all of the method's predictions must be reversed in order to utilize its power, thereby moving the result above the random guess line. Detection error trade-off graph. An alternative to the Roc curve is the detection error trade-off graph, which plots the false negative rate versus the false positive rate on non-linearly transformed x and y axes. The transformation function is the quantile function of the normal distribution i.e., the inverse of the cumulative normal distribution. It is, in fact, the same transformation as Z.Roc below, except that the complement of the hit rate, the miss rate or false negative rate, is used. This alternative spends more graph area on the region of interest. Most of the Roc area is of little interest. One primarily cares about the region tight against the y-axis and the top left corner, which, because of using miss rate instead of its complement, the hit rate is the lower left corner in a det plot. The det plot is used extensively in the automatic speaker recognition community, where the name det was first used. The analysis of the Roc performance in graphs with this warping of the axes was used by psychologists in perception studies halfway the 20th century, where this was dubbed double probability paper, Z-score. If a standard score is applied to the Roc curve, the curve will be transformed into a straight line. This Z-score is based on a normal distribution with a mean of 0 and a standard deviation of 1. In memory strength theory, one must assume that the Z.Roc is not only linear, but has a slope of 1.0. The normal distributions of targets and lures is the factor causing the Z.Roc to be linear. The linearity of the Z.Roc curve depends on the standard deviations of the target and lure strength distributions. If the standard deviations are equal, the slope will be 1.0. If the standard deviation of the target strength distribution is larger than the standard deviation of the lure strength distribution, then the slope will be smaller than 1.0. In most studies, it has been found that the Z.Roc curve slopes constantly fall below 1, usually between 0.5 and 0.9. Many experiments yielded a Z.Roc slope of 0.8. A slope of 0.8 implies that the variability of the target's strength distribution is 25% larger than the variability of the lure strength distribution. Another variable used is D, which can easily be expressed in terms of Z values. Although D is a commonly used parameter, it must be recognized that it is only relevant when strictly adhering to the very strong assumptions of strength theory made above. The Z-score of an Roc curve is always linear, as assumed, except in special situations. The Yohnlena's familiarity recollection model is a two-dimensional account of recognition memory. Instead of the subject simply answering yes or no to a specific input, the subject gives the input a feeling of familiarity, which operates like the original Roc curve. What changes, though, is a parameter for recollection. Recollection is assumed to be all or none, and it trumps familiarity. If there were no recollection component, ZROC would have a predicted slope of 1. However, when adding the recollection component, the ZROC curve will be concave up with a decreased slope. This difference in shape and slope results from an added element of variability due to some items being recollected. Patients with anterograde amnesia are unable to recollect, so the Yohnlena's ZROC curve would have a slope close to 1.0. History. The Roc curve was first used during World War II for the analysis of radar signals before it was employed in signal detection theory. Following the attack on Pearl Harbor in 1941, the United States Army began new research to increase the prediction of correctly detected Japanese aircraft from the radar signals. In the 1950s, Roc curves were employed in psychophysics to assess human detection of weak signals. In medicine, Roc analysis has been extensively used in the evaluation of diagnostic tests. Roc curves are also used extensively in epidemiology and medical research and are frequently mentioned in conjunction with evidence-based medicine. In radiology, Roc analysis is a common technique to evaluate new radiology techniques. In the social sciences, Roc analysis is often called the Roc Accuracy Ratio, a common technique for judging the accuracy of default probability models. Roc curves are widely used in laboratory medicine to assess diagnostic accuracy of a test, to choose the most optimal cutoff of a test, and to compare diagnostic accuracy of several tests. Roc curves also proved useful for the evaluation of machine learning techniques. The first application of Roc in machine learning was by Spackman, who demonstrated the value of Roc curves in comparing and evaluating different classification algorithms.